Okay, in our previous segments, we were talking about Kepler's laws. And Johannes Kepler only knew about elliptical orbits. So he knew that a planet would go around a star in an elliptical orbit. But along comes Sir Isaac Newton, and he was able to prove that there are other kinds of orbits were possible too. And so this should be a review that you learned that there were two kinds of mechanical energy. One kind was called kinetic energy, and another kind was called potential energy. So kinetic energy, E sub k, was equal to 1/2 mv squared. So m is going to be the mass of the object that's moving, like a rocket ship. V is going to be the speed of the rocket ship, and it's 1/2 mv squared. Notice that it's always a positive number. Even if you were going backwards, so that you had a negative speed, what happens when you square a negative number? You get a positive number. So this thing is always going to be a positive number. Then you got the potential energy. So potential energy depends on position, depends on where you're at. So Sir Isaac Newton came up with that formula there for the potential energy of an object. And so it was equal to negative big G m1. So m1 could be the star, and then m2 could be the planet, or m1 could be a planet, and then m2 could be a rocket ship. Okay, so we've got two masses, and then r is going to be the distance between them. And that was the potential energy. And notice it's always a negative number. Okay, so kinetic energy is always a positive number, and then the potential energy is always a negative number. And then we learned that when energy is conserved, we add together the two energies. So you've got the kinetic energy plus the potential energy is going to be equal to the total energy. So a rocket ship has both kinetic energy because it's moving, and it's got potential energy because it's a certain distance from whatever it's orbiting. So we put these two numbers together. Now, can you see that it would be possible that if this number, whatever it is, let's say it's 7, if it's bigger than this number, so let's say that this is a negative 5, can you see that when you add the two numbers together, you get a positive number? But what about if this was a 7 again, but this thing down here was a negative 9? Then when you add the two numbers together, you get a negative number. And could you imagine that maybe this thing's a 7, and then this thing is a negative 7, and then when you add the two numbers together, you get a 0. So these three possibilities, a positive total energy, a negative total energy, and a 0 total energy, are going to correspond to different kinds of orbits. So here's a thought experiment that Sir Isaac Newton did. He pretended that here's the Earth, and then put a cannon up here. So here's a cannon that is going to fire a cannonball shell. And if it doesn't have enough speed, it will crash into the Earth. But in actuality, it went into orbit. It's just that the Earth got in the way. So that if somehow the cannonball could turn intangible, like the Vision from the Avengers, so if this cannonball could travel into the Earth it would go around the core of the Earth, and then it would come out over here somewhere, and then it would come up behind the cannon and then shoot past it again. So this is actually an orbit. It's just that the Earth is getting in the way. Now, let's give the cannonball more speed. So if it had more speed, can you imagine that it might even be able to go completely around in a circle? So what speed do you think that would be? The circular speed. So if a cannonball has a circular speed, it goes in a circular orbit around the Earth. Now, it still can't escape, but it has now can go completely around. So that means the International Space Station has a circular speed. It has to be going at a circular speed in order to completely orbit the Earth and not crash into it. Okay, but what would happen if you give it more speed? So if you give it more speed, then the circle turns into an ellipse. Okay, let's give it more speed. So if we give it more speed, it can escape. What do you think we should call that speed? The escape speed. So if a rocket has escape speed, it can escape the gravity of the Earth. And then you could even go faster than the escape speed. So if you're going faster, it has this kind of orbit, which is going to be called a hyperbola. So this one's a parabola, and then this one is going to be a hyperbola, and then this one is going to be the ellipse. So you have different kinds of orbits. There are 3 kinds of orbits that a rocket can have, and it all comes really down to who is winning. Is the speed winning, or is the gravity winning? So in the case of where it has a elliptical or circular, or it's bumping into the Earth orbit, what's winning? Gravity. It can't escape the gravity of the Earth, so this is a closed orbit. Johannes Kepler knew all about elliptical orbits, but he didn't know about these 2. And so if the speed is winning, then it's this one. So you have more than enough speed in order to escape the gravity. And then what's the third possibility? It's if the 2 of them are exactly balanced, and then that turns out to be this one right here. Okay, so let's take a look at the different kinds of circular and escape speeds that are possible. So for the Earth, if you want to go in a circle around the Earth, you have to be traveling at 7.9 kilometers per second. If you want to escape the gravity of the Earth, then you have to be going at 11.2 kilometers per second. Look at the moon. Do you notice that the 2 numbers are smaller? Why? There's less gravity on the moon. And so this is one of the reasons why we would like to have a moon base, is we could build and launch rockets from the moon, and then it would take less energy than trying to do it from the Earth. Then look at Jupiter. Well, you definitely don't want to be launching a rocket from Jupiter because it's got more gravity. And then the sun, look at that. So that would be the energy it would take to escape the gravity of the sun from its surface. And then you also have the escape velocity for the Milky Way galaxy in which we live in. Now, if you're wondering, well, where in the world did all those numbers come from? So it can be shown, and I will show you in the appendix, which you don't need to know if you're one of my students for the exam, where the formulas come from. But there's a formula for the circular speed and then there's the formula for the escape speed. Okay? All right, let's take a break. And when we come back, we will talk about the theories of relativity.